Alright, we're going to talk about electron configuration. Let's do this. To start off with, we need to go back to about 1908 to 1913, and that is when our boy Rutherford was developing his idea of what an atom was. And this is during the time of the gold foil experiment, where scientists figured out that basically the atom consisted of a very small, very positively charged, dense nucleus in the middle, and then there was all this space between the nucleus and these electrons just whizzing around the outsides. And this was later added to by some guy named Bohr, and his idea, which later became the Bohr model, said, I like your idea, Rutherford, but let's have the nucleus in the middle, let's have the electrons going outside just like you did, but let's have the electrons in these neat little shells. So this little atom right here, which 3 electrons, which would be, by the way, lithium, would have 3 electrons. It would have 2 in the first shell, and then there would be up to 8 it could have in the second shell, and then so on and so forth. But since it only has 3, it would have 2 in the first, and then 1 in the third. And this made it very easy to organize and figure out how many electrons there were. But it turns out it's entirely and totally wrong. These guys were both really wrong, and what we now believe is something known more as the quantum mechanical model, which basically takes away the nice shells and adds these blobs of probability. This is where we think electrons are. Instead of saying in different little rings around an atom, I have different shells. So there's the or orbitals. There's the s orbital. There's the p orbitals, plural. There are 3 of them. There are the d orbitals. Again, there are 5, and there are the f orbitals, of which there are 7 orbitals. These are all just sort of probability zones that we think electrons could be in this area. It's kind of like if you ride a bus home or to school, your parents might know the name of the bus, but they wouldn't know where you were in that bus exactly. They may not know exactly where the bus is. They just know that you're in that kind of bus going towards school. That's kind of like with this. So if I have this one right here, maybe I know one electron is right in this little pod right here. That's like your parents knowing that you are in a school bus going to school or going from school, but they don't know exactly what street you're on or exactly what seat you're in. And so this later led to us being able to use the electron configurations for more precise determinations of exactly where electrons were per atom that you were talking about. And there are a few rules that go along with that. And so the first one I want to point out is called the off-ball principle. Off-ball is German for to build up or building up. And basically what it says is that I have electrons that I'm putting into these orbitals or these shells. Again, these shells, I'm putting electrons into them, and it turns out that certain ones have less energy, or have less energy than the other ones do, and so it wants to fill those ones first. So it always fills the lowest available energy levels before filling up the higher ones. Now, what that leads to, what we can't really care about, is what's sometimes called an off-ball diagram. And so with my bus analogy, we're going to go back and call all of these orbitals, these are just different school buses. And they're just named this way. So you might ride bus 14 or bus 4 or purple bus or whatever bus you might name, whatever they've named it. These are just different names of buses. So this is the 1S bus, this is the 2S bus, this is the 3D bus, this is the 5P bus. And certain buses take less energy to move, or less fuel, or however you want to go about it. And the way you read this diagram is you write 1 to 7, and then you write 2 to 7, and then 3 to 6, and 4 to 5, and everything in the first column is an S, everything in the second column is a P, the third column is a D, and the fourth is the letter F. And you go at a diagonal, so I start from the top right, and I read all the way down to the bottom left. And so the very first bus in line is the 1S bus. And then I jump back up to the next one, and I read diagonal again. So then comes the 2S bus. Then I go again, and next comes the 2P bus, or the 2P orbital, and then the 3S. And so far this is making pretty much good sense. And then we jump to the fourth one, and this is where things get weird. We go 3p, but instead of going to 3d like you might expect, we go to 4s. And it turns out that the 4s orbital takes less energy to occupy than the 3d orbital does. Imagine having to balance a certain number of um, just ping pong balls in your hand or billiard balls or whatever. It's easier, takes less energy to balance one than it does to balance two or four or seven. Takes more energy to do the higher one. So if you had to do it, it's much easier to balance a lower number than a higher one. I personally like this one over here, this model. It's the same thing, but it sort of shows you kind of like a board game where you start here. There's only one point to start, and then you just sort of keep continuing through, going back up the dotted lines, and then back down, and then back up. And so you'd read 2p, and then 3s, and then you do 3p, 4s, and then 3d, 4p, 5s, 4d, 5p, 6s, 4f, 5d, 6p, 7s, 5f, 6d, and 7p. And I did not need to read all of that, but I did. So anyway, that's the off-ball principle. It just basically means you use this chart, and it tells you which orbital comes first, or which bus gets loaded first when you get and the electrons leave school that day. Continuing on with our bus analogy, Hund's rule says that every orbital in a subshell is singularly occupied before it is doubly occupied. And so what that means is I have a little bus here. We'll call this a little bus. This bus has 3 seats, 1, 2, 3. This represents a p orbital. And in each of these seats, I can fit 2 electrons. If you go back to this image here, imagine each one of these little blobs is a bus seat. And each bus seat can fit 1 person. So 1, 2, 3, 4, 5, 6. 6 electrons will fit on this p bus. And that's kind of where we are here. So instead of those different axes, we just see a box, and instead of the 2 blobs, I have sort of 2 blank spaces they could fit in. And so what this means is you come in, and I'm going to talk about the empty bus seat rule. Imagine this is a bus with 3 seats, and you're the first one on the bus. You pick 1 seat. Doesn't really matter. You just pick 1. And the second person comes on the bus, and they're going to pick not to sit with you. They're going to pick their own bus seat because they want to stretch out their legs. So they go to the next bus seat. And then the third guy that gets on the bus, well, the first 2 are taken, so he's going to go to the third seat, and he's going to sit there first. And then comes the 4th person on the bus, and he now does not have his own seat because you've occupied, the first 3 have occupied the seat, so they have to go now and sit at a different seat. And you have these up arrows and you have these down arrows, which I'll get to in just a second. And so an example of a correct one, this, by the way, would be 7 electrons, 2, 4, and then 3 is 7, which would be nitrogen, actually. This is nitrogen. Has 7 electrons, at least a neutral version of it does. So the correct way would be to draw an up arrow for the 1s and then a down arrow for the 1s, because the s buses only have 1 seat. It's kind of lame. It's a very, very short bus. And so the first guy gets on the bus, has his own seat. The second guy can't have his own seat, so he has to sit next to the guy. And then the 2s bus, it's still an s bus, so it still has just 1 seat, so the first guy sits there, the second guy has to sit next to him. And then for the 2p bus, this bus has 3 seats, so 1 guy sits there, 1 guy sits there, 1 guy sits there. It is very easy and also very wrong to get used to drawing up arrows and down arrows and go up, down, up, down, up, down, up, and move on. Again, this is wrong. Don't do this. We picked the order of the buses, 1s, 2s, 2p, using the off-ball principle. So 1s comes first, and then 2s, and then 2p. That's kind of where it comes from. Now, there's a side note here I want to talk about. There's another rule called the Pauli exclusion principle. And what that says is that I can never have 2 up arrows or 2 down arrows in the same bus. To go back to my bus seat analogy, a bus seat has a window seat and it has an aisle seat. And you can either sit next to the window or sit next to the aisle. You can't do both. I don't have a good way to say you can't do both, but you can't do both. You cannot have two people sitting in the window seat, and you cannot have two people sitting in the aisle seat. And so, if you have two up arrows, that would violate the Pauli exclusion principle. If you have the two down arrows, again, that would violate the Pauli exclusion principle. So, I have a quick check for you, to see if you've been paying attention here. Which of the following is a correctly written electron orbital? And I will give you 5 seconds to think about that. So, here we go. Oh boy, that was intense. So, which of the following is the correct orbital? It is, in fact, C. And let's just go through this. So, letter A here. This first one is correctly one up and one down. By the way, sometimes the notation only draws half an arrow. I don't know why, they just do. But this one right here, the up arrow is good, this up arrow is good, but this down arrow should not be here. This violates Hund's rule. This should always be its own bus seat first. Letter B shows the first one good, and then the second one violates Hund's rule because this should be in its own bus seat, and it violates the Pauli exclusion principle, which says that this should never have two up arrows. We should always have one up and one down in the same thing. By the way, the up and the down arrows represent the spins of electrons. Basically, one spins one way and one spins another way, and they kind of turn themselves into little magnets. And two up spins would actually repel each other, and two down spins would repel each other. Kind of like having a north and a south magnet together. And so, if it helps you think instead of up and down, think of north and south magnets, then the idea works the same. D is incorrect for the first one. This would be a P bus right here because there's 3 boxes. This would be correct, but the first one would violate that Pauli exclusion principle, leaving C as the correct choice. Now here is a quick view of some other ones. These are the first few lighter elements that we have with the electron configurations written out, as well as the orbital diagram, this is sometimes called. So again, the way I get the 1s, 2s, 2p, 3s comes from the off-ball principle. It just comes from using that chart and saying which comes first. I have, for lithium, 3 electrons, so I have 1 up, 1 down. That gets this box full. Once this bus is full, I can move on to the next bus, and I have 1 more left, so it's just 1, and then that one's done. And the way we write these out, once we've kind of gotten this down, is I'm just going to make a list, sort of like a list of all the buses. The name of the bus, 1s, and then how many students are on that bus, in this case 2. So this first box is a 1s bus, and there are 2 arrows, so 1s2. The second bus is called 2s, so we're at 2s, and there are 1 electrons on there. There's 1 student on that bus, so I put a 1. And you can kind of see how this goes down with 4, there being 4 arrows, 7, there's 7 arrows, 11, there's 11 arrows. And all these little numbers here, the 2's, not the big ones, but the small ones, the exponents, those should all always add up to the number of electrons that you have. So, ending with a bit easier to read example, here we have an electron configuration. Again, this comes using my off-ball principle. The s orbital holds up to 2 electrons because there's sort of 1 blob, and each blob can hold 2 electrons. Or it's like saying there's 1 seat on the bus, and each seat holds 2 students. The P bus has 3 seats, which holds 6 students, and the D bus has 5 seats, which holds 10 students. And so for argon, right here, which has 18 protons, and so a neutral atom of argon would have 18 electrons to match those protons, because there's no charge involved just yet. And so the first one I need to do, I need to fill up the 1s bus, and so 1s2 gets filled up because there are 2. And then the 2s comes in, gets filled up with 2 electrons. That gives me 4 total. I need another 14. And so then I add the 2p is next, and it fills 6. That brings me to 10 total. The next is a 3s bus, and 2 more jump on that. That gets me to 12. And then after the 3s, I jump over to the 3p, and that fills me up with a total of 6 electrons, which fills up to the top, giving me 18 total down here. So this is a brief electron configuration chart walk through. I hope this helps, and have a fantastic day.